Well, again, there were three things. One was the complement system. And early on, through my experience with Manfred Mayer, I had learned to do assays for the components of the complement system that were exquisitely sensitive. So as we began to work on the amplification part of the complement system, we were able to design exquisitely sensitive hemolytic assays, which allowed us to purify the critical proteins, which were present in plasma in very small amounts. And so with Doug Farron in particular, but also with Sean Ruddy and Irma Gili, we were able to define this amplification loop, which creates all the pathobiology as well as the host resistance part of the complement system. And that, for me, is one of the major accomplishments. One of the things that has happened 20 years later was that one of the proteins that we purified at that time turns out to encode the gene for age-related macular degeneration. Now, that's a fabulous example of how basic science can have tremendous implication for human disease that has absolutely nothing to do with why you did the basic science. And it's why I have some reservations about the current, in my view, overemphasis on applied, that you quickly run out of things to apply, and you often don't know what to apply. And I think the major advances in medicine have mostly come from the knowledge that was created and then taking advantage of that knowledge using other technologies. And I think finding that factor beta 1H, which regulated the amplification system, was the gene that determined more than 50% of patients with age-related macular degeneration is a wonderful outcome, quite separate from the progress that's been made in, building on the real purpose of doing their research. The SRSA that I mentioned to you earlier, I became very preoccupied with that, and with Jeffrey Drazen, editor of the New England Journal of Medicine now, we worked out a great deal of the pharmacology of that molecule, began to make real progress in the purification with a young man from MIT who was in their analytical chemistry group by the name of Bob Murphy. And I knew that it was not a typical protein and I was not going to be able to do it as an immunologist. So I went to talk with Klaus Beeman at MIT, and he was busy analyzing the moon rocks. So he said to me, I can't help you, I'm too busy with the moon rocks, but I've got this very excellent young postdoc who I think could help you work on this project, and that was Robert Murphy. And with Murphy working on it, then we obtained an excellent characterization. And Murphy then took a sabbatical in Sweden with Bengt Samuelsson and worked out the actual composition of slow-reacting substance. And as soon as he had the composition, E.J. Corey in the chemistry department at Harvard made the molecule for all of us because it had a lot of double bonds. And so E.J. felt there would be more than 100 stereoisomers. And he said, the best thing is you guys do your best purification. I'll synthesize what I think are the candidates. And when the molecule I synthesize is exactly as active as the one you purify, we'll have the right structures. And that's what we did. So that I was disappointed that I wasn't there at the end when we got the composition, but at least it was somebody I had trained. And so my lab, we then immediately moved to take advantage of that, to purify the enzyme that made it, and then to clone the human enzyme for the first time, and then to go on and make mice with various deficiencies and really work out that pathway. So that's the second area. It's now called cysteinoleucotrienes. And the third area that I continue to work on is the mast cell. And I would say to particularly focus on what the mast cell makes, both preformed and newly generated, and what its role is in biology. So I'm still working on the same 3 projects I was working on as a postdoctoral fellow. It's just 50 years later, and we can do a lot more.